Welcome to chapter 7.3, 7.4, ACE, acids and bases. Now we're getting to the fun stuff. We're looking at these corrosive materials that burn away hands and are in the blood of aliens and all this kind of stuff. So acids are corrosive substances. They have a wide variety of meanings that has changed over hundreds of years from one thing to another and to another and to another. At this point, really all I want you to know is that there are such things as acids and that those acids are sour-tasting, corrosive, materials, often liquids, okay? So examples of acids are like, ant stings and bee stings and sulfuric acid in car batteries, and fruit has some acid in it, and vinegar is obviously an acid as well. So we use acids for a variety of things, from eating it to allowing our car battery to operate to, if we're an ant, to sting humans. Bases, on the other hand, are the opposite. They're bitter tasting rather than sour. Not that you should really taste them in my lab. No eating in my lab, just a reminder. They're slippery or soapy to the touch. And then they are corrosive, especially things like, sodium hydroxide, which is like caustic soda, which is used in cleaning products and things like that. But, when you think of bases, I want you to think of like soap and shampoo, toothpaste, dishwashing liquid, and things like that. Ammonia in floor cleaners and that kind of stuff. These are the stereotypical bases. And there's one other word I want to make you aware of, and this is alkali. The idea of sometimes we call bases alkalis, and sometimes we call them bases and whatever else, and sometimes they're used interchangeably, but they're really not. Bases are the sour, shampoo, touch, whatever else, and alkalis are a subsection of that, and those are the ones that can be dissolved in water. So a lot of bases are alkalis, but not all of them. There are some bases that cannot dissolve in water, but most of them can. Alkalis, bases that can dissolve in water. Acids and bases. Great, let's move on to the next section. So what we're looking at here is the pH scale for acidity. Down here, at the 1, 2s, and 3s and 4s, we have acids, and up here in the 10s, 11s, 12s, and 13s and 14s, we have bases, okay? So, examples that we've got here is hydrochloric acid, lemons, Coca-Cola, vinegar, and this kind of stuff. And up the other end, we've got caustic soda, ammonia, oven spray, Jif, and Ajax, and all this kind of stuff, okay? And what we've actually got down here, we've got a colour chart, okay, from deep red up to, blue. This is something called an indicator. It's like this one in particular is called the universal indicator. And if you drop some of this universal indicator into one of these substances, it'll turn us to a particular colour. And then from that colour, you'll be able to tell what acidity that is. So it's a very useful chemical that we can use to find out how acidic or how basic a chemical is. Okay? So one other section that we haven't really talked about is this bit in the middle. This is neutral, and pure water is supposed to be precisely 7. The tap water that you have is usually a little bit basic, so it's a little bit above 7 often, or maybe it's a little bit acidic at times, so it might be a little bit below 7. But basically, absolutely pure H2O would be right smack bang on 7 pH. So, now, neutralization. Let's talk about that. Okay, neutralization. This is acid plus a base causing salt and water. So, this is what we mean by that. Let's say we drop an acid on the table. Okay, during one of our pracs, we drop an acid on the table and we want to get rid of it. What we can do, we don't want to burn our hands, so we drop some base on top. Okay, so the acid plus the base react together, forming a salt plus a water. So it might go from the acid being a pH of 2 or something, And after the reaction, the acid and the base should react together and make a pH of 7. All right, and pH 7 is like water, so it's pretty safe to clean up. Okay, and that's basically how a neutralization reaction works. So let's look at some examples of acids and bases. Here we have hydrochloric acid. The hydrochloric acid is used to clean surfaces of iron, make it nice and shiny, food processing, manufacture of chemicals, and oil recovery. Okay, nitric acid, manufacture of fertilizers, dyes, drugs, and explosives. Sulfuric acid, very useful in fertilizer, plastics, paints, drugs, detergents, and paper, petroleum refinery, and metallurgy. Citric acid, it's a pretty, what one might call a natural acid, I suppose. Citric acid, citric fruit in oranges and lemons, but it's also used in the food industry and the manufacturing of some pharmaceuticals when it's at high enough concentration. Carbonic acid, whenever you dissolve carbon dioxide in water, so in like a fizzy drink or like a Coca-Cola or something, that's what's formed, carbonic acid. So it's not existing as a gas inside the liquid, it's forming carbonic acid. Acetic acid. Acetic acid is vinegar. It's used in a variety of other chemical reactions, including aspirin and things like that as well. Sodium hydroxide. It's a caustic soda. It's soap, basically. Cleaning agent and whatever else. And now ammonia, manufacturing of fertilizers and cleaning agents. A lot of floor cleaner has this kind of stuff. And good old sodium bicarbonate to make cakes rise and, you know, yummy things like that. Okay, so let's move on to something different. What we're looking at here is our first chemical acid-base reaction. Okay, so what we've got here is we've got hydrochloric acid plus sodium hydroxide forming sodium chloride and water. Okay, so this is a common acid-base reaction. All right. Furthermore, it's a common hydroxide reaction. This is how hydroxides often form, often react. Okay, so we have HCl over here plus sodium hydroxide forming sodium chloride plus water. Okay, well, HCl. So, the sodium here is reacting to the chlorine and forming sodium chloride. The hydroxide is reacting to the hydrogen and forming water. And that's a common reaction. And what you'd find is it doesn't have to be sodium hydroxide here. It can be potassium hydroxide or whatever other kind of hydroxides. Okay, it would always, if it was potassium hydroxide, the potassium here would react to the chloride, being potassium chloride, and then the hydroxide would react to the hydrogen, making water. Okay, so this is the first type of reaction. And as it's kind of forming a salt and water, you know, the only way you can really see it is with universal indicator or some kind of indicator. So the next type of reaction we're going to look at here is when you react an acid to a metal. So you have hydrochloric acid, there's hydrochloric acid in here, and just a sheet of magnesium. This is pure magnesium being dropped into hydrochloric acid. All right, let's have a look to see how that one looks. Hydrochloric acid plus magnesium causing magnesium chloride plus hydrogen gas. Now, so that means all this bubbles and gas you can see kind of flying off here, that's hydrogen gas, and you can actually set that on fire, which hopefully we'll do in a prac or a demonstration at some point. But this is true, again, this is a general rule. So hydrochloric acid or some kind of acid with some kind of metal, and it doesn't matter what kind of metal it is. You know, iron, hydrochloric acid plus iron would be iron chloride plus hydrogen gas. All right, and you can always do a pop test to see the hydrogen kind of forming off there. The last kind of reaction we're going to look at is what's called a carbonate reaction. Okay, so I've switched these around for some reason, but don't worry too much about it. So here we have calcium carbonate plus hydrochloric acid, calcium chloride plus water plus carbon dioxide. Right, so this is a really interesting reaction. And the reason why it's so interesting is because it's causing so much damage. The carbonate reaction, this kind of carbonate reaction is often seen in acid rain. It's caused by coal manufacturing. A lot of the gases you see coming off from coal mines and, sorry, from coal power stations causes this kind of hydrochloric acid to be kind of flying around, you know, in clouds, and it comes down as rain. Now that's fine. It's a bit strange, but all right. But what happens when you hit, you know, things like this calcium carbonate statue that's basically, you know, entirely calcium carbonate. So there's a period of less than, I think it's like 30 years, the difference between, 60 years, sorry, the difference between these two photos. So this was 60 years before this photo. You can see the damage that's been done. You know, you can clearly see the face and the hand and whatever else of the statue. And it's been totally eaten away by acid rain. And that's the damage it can do, not only to our statues, but I mean, this is the effect it's having on the statue. You can imagine the effect it's having on our rainwater, on, you know, our natural environment and our lakes and things like that. So it's causing all sorts of trouble. One way that they're working to solve the problem is to actually put calcium carbonate as a descrubber on the top of these power stations. So before this hydrochloric acid flies out the top of your power station, they have some calcium carbonate sitting there as a descrubber to absorb, you know, to make this reaction occur before it ever gets out into the environment. And as a result, you know, coal power stations are now a lot cleaner than they used to be. They're still pretty bad, but, you know, they're a lot cleaner than they used to be. Okay, so now what I want you to do is I want you to go to chapter 7.3 and 7.4 and look at the blue words, copy them up onto Quizlet, and I'll see you in class.